All right, so hello everyone. My name is Emmanuel. I'm from the Cornell database group, and I'm gonna tell you a little bit about one of our recent projects, which is called SkinnerDB. What I'm gonna present to you with, hello? Was there a question or? Okay. So what I'm gonna present to you mostly relates to the Sigmod paper from 2019, but I'm also tell you a little bit about more recent results and some ongoing work that we currently have about this project. So SkinnerDB generally focuses on query optimization, a topic that I have been working on quite a bit. And typically in a database system, the query optimizer has some kind of component which enumerates candidate plans for a given input query for processing it. And then it uses a cost model in order to predict the execution cost of those plan candidates and tries to select the plan with minimum estimated execution cost. Now, every once in a while, query optimization goes horribly wrong and we end up with a plan which has a cost many orders of magnitude higher than necessary. And if that happens, it's often due to problems in accurately predicting the execution cost of a plan candidate, because traditional database systems, they make a lot of simplifying assumptions in estimating execution costs. For instance, they assume independent, uncorrelated query predicates and uniform input data. And if those assumptions do not hold, then all bets are off essentially. So our goal with SkinnerDB was to create a system which makes essentially no assumptions about the query or about the data and still provide some kind of formal guarantees on achieving at least a near optimal expected execution cost. And we achieved that by a process that we call intra-query learning that differs from a lot of other ongoing work on leveraging machine learning for query optimization, which focuses on inter-query learning, which means that we learn from past queries in order to optimize the next query. But this is not what we are doing. What we are doing is that we learn from scratch during the execution of the current query. And what we learn, we apply it directly in order to improve the remaining execution of the current query. So that's why we call it intra-query learning. And the advantage, of course, is that we do not need any training data beforehand. We don't need any representative workloads, but we can optimize one query on a fresh data set using some user-defined functions that we have never seen before, for instance. And given enough data, we still converge to optimal planning decisions. Now, intra-query learning is used in one out of multiple query evaluation phases that we perform for each incoming query. In the first stage, we would, for instance, apply all unary predicates on single tables. Then we would create some auxiliary data structures that help us to speed up the following joins. Then we perform the join phase, which I'm gonna detail a bit in the following, where we use intra-query learning. And finally, we use grouping and aggregation. So the main technical contribution is on the join phase, and the join phase works at a high level as you see here. So in the join phase, we essentially decompose the input query into many small evaluation time periods, which we call micro episodes. And in each micro episode, we first of all select some join order to try next. Then we execute that join order for a fixed number of steps, which at the same time generates result fragments that we collect. And also it gives us some unbiased sample for the quality of a join order, which we analyze and from which we learn to select better join orders in the coming episodes. Query evaluation stops once we have collected one complete query result, which might have been stitched together from result fragments generated in different episodes, perhaps according to different join orders. And one important thing for our approach is that this whole iteration happens with a very high frequency. So we would typically have 10,000s to 100,000s of micro episodes per second. So that is pretty fast. And it also means that we want to use some specialized join operator in order to make it efficient, which I'm going to introduce in more detail later. All right. So that is the high-level principle. In the following, I'm first of all going to talk a little bit more about the learning component. Now, the high-level scenario that we have here matches the scenario of reinforcement learning, where we generally have an agent which performs actions on some environment, and from those actions result rewards. Now, the goal of the agent is to maximize the rewards obtained, but at the beginning, the agent does not know which actions or action sequences are associated with what expected rewards. Therefore, the agent faces the so-called exploitation versus exploration dilemma, which means the agent can decide to be curious and to explore new action sequences about which little is known, or the agent can decide to be greedy and to try to exploit action sequences that currently seem to work pretty well in comparison. So there's this tension, and the area of reinforcement learning has produced a couple of algorithms which optimally balance between those two extremes and can even make formal guarantees that the expected reward collected over time actually is near optimal. And we want to leverage that for the domain of query evaluation. Here, the agent is our database system SkinnerDB, and one action corresponds to trying one join order for one episode. The environment is defined by query and by data properties, and we will define rewards as being proportional to query evaluation progress. And I'm gonna tell you more later about how we define that precisely. Now here again, we have the trade-off between trying join orders that currently seem to work well versus trying join orders about which little is known. And if we link reward to evaluation progress and use one of those algorithms which guarantees to converge to optimal expected decisions, then we should be able to leverage that for near optimal expected evaluation progress. Now, this is the high-level picture. More precisely, we use one algorithm from the area of reinforcement learning, which is called the UCT algorithm, and that stands for upper confidence bounds on trees. So as the name suggests, the algorithm represents the search space for optimization as a search tree. So in our case, the search tree represents a possible join order choices. And then one path from the root node to one of the leaf node corresponds to one specific join order. Now, this algorithm maintains statistics about the confidence bounds on the average reward that can be obtained with different join orders. And since it is the upper confidence bounds algorithm, it focuses on the upper bound of that confidence bound when selecting the next join order to try. So here in each episode, we start from the root node here, and we select the child node, which has the highest upper confidence bound. So that's an optimistic estimate of the quality for the corresponding subtree. And we continue doing that here after selecting table R as first table. We would select table S as second table in our join order. And now for this simple query, we are out of choices. We have to select T as the last table in our join order. And by balancing between the exploration and exploitation, this algorithm actually converges to near optimal expected rewards. Now, one concern that people often have at this point is that for a given query, the space of all possible join orders can actually be large. So just creating the search tree might already come with a significant overheads. That's why we do not do this. Instead, the UCT algorithm starts with a small tree, and then it grows it gradually over time into the direction of the join orders that currently seem interesting. Now, let's make things more concrete by a little visualization. So here I'm visualizing how SkinnerDB processes one query from the join order benchmark. And what you see here in this video that I'm about to start is the UCT search tree. we have slowed down the video at the beginning significantly, so this doesn't correspond to real time. Now I'm gonna start it. So here we start with one single join order, and now the algorithm expands the search tree. At the bottom, you see the average reward associated with different join orders, and the color of the nodes represents the frequency at which they are currently selected. And those green lines over here, they represent a query evaluation progress along specific join orders. So once the green line completely connects the root node to one of the leaf nodes, then query evaluation has stopped. And here you see that we are approaching that case. We have pretty much converged to one join order, it seems, and now query evaluation stops. On the left upper corner, you see that we have performed about 6,500 micro episodes, which in real time would take at most a few seconds. So this is significantly slowed down. All right. Now, I already announced that in order to make this process efficient, we want a specialized execution engine. Let's see what kind of properties we would like from that execution engine. So here you see some kind of wish list that we have for the execution engine in order to support this reinforcement learning approach well. Now, the first thing that we want to converge to optimal join orders. So after executing a join order just for a few steps, we want to get some unbiased sample for the quality of that join order. Also, we want to switch between different join orders with a high frequency. So we need to keep the overheads for switching between join orders very low. And also, since we want to keep trying and switching between hundreds or thousands of join orders for one query, we need to keep the intermediate result state per join order fairly small, because otherwise we run out of memory. Now let's see how standard execution compares to that wish list. So with standard execution, let's say that we join those 4 tables here in a join order from left to right. So we would start by reading the first table, perhaps building a hash table over it. Then we would read the second table, perhaps we would probe the hash table, and that would generate one intermediate result. And afterwards, we might still have a little bit of time to start looking at the third table, but at some point, the current micro episode will probably end. Now, the first problem here is that I have a lot of information about the cost of the first few joins, but I don't have any information about the cost of the remaining joins. So I cannot say anything about the overall quality of the current join order. And that means we don't really have early quality feedback. Now, another problem is this. Let's say we want to switch from this join order to a different join order, which might actually generate different intermediate results. Now, the question is, what do we do with this intermediate result at the switch? Now, a first possibility is that we discard the result at the join, but then when selecting the same join order again later, we would have to regenerate it. And also there's some overhead in deleting large results. So overall, we wouldn't have low switching overheads. Now, of course, there's also the possibility that we just keep the intermediate result when we switch to a different join order. But that would mean that we might have to keep lots of intermediate results for the different join orders in memory or on disk. And that means that the execution state per join order might actually be large. So the standard join execution is probably not a good idea when comparing to this wish list. This is why we introduced a specialized join algorithm that is tailored to support our reinforcement learning approach. And I'm going to illustrate how this join algorithm works by an example. It's a multi-way, so-called depth-first join algorithm, which essentially joins all of those tables in one operation. Now, when joining those tables, we start looking at the first tuple in the first table in join order. And after that, we immediately proceed to the second table in join order, and we look for the first matching tuple, meaning the first tuple that satisfies all applicable join conditions for the currently selected tuple in the first table in join order. After we find a matching tuple, we immediately proceed to the next table in join order, and we find the first matching tuple here, which means the first tuple that satisfies all applicable join predicates with the currently selected tuple in the first and in the second table. And then we proceed to the last table. Once we find a matching tuple here, it means we have found a combination of tuples that form a join result tuple. So we add that as result fragment to our result set. And we continue looking for matching tuples in the last table. Here we find another one, we add it to the result as well. And now we have considered all tuples in the last table. So we decide to backtrack and go back to the third table in join order. Perhaps we didn't have enough time to look at the next matching tuple in the third table, but at some point the episode will end. Now let's see what we have gained by this join algorithm. Now, the first thing is that in order to capture the current execution state completely, all I need to store is the currently selected tuple in each of those base tables. So essentially one record ID per table. So we definitely have small execution state per join order. Also, if I want to switch from this join order to a different one, the only thing that I need to do before restarting the join algorithm is to reset those counters for each of the tables. So at most, I have to change one record ID for each of those base tables, and doing that is also fairly quick. So I have relatively low switching overheads as well. Now, the final point is a little bit more involved. I want to converge to optimal join order. So I need something like an unbiased quality estimate after executing a join order just for a few steps. The basic idea here is to measure the query evaluation progress per join order and use this as a sample for the quality of a join order. Because the join order, which has in average the highest evaluation progress per time unit, is also the best join order. Now, the question here is, how do we define query evaluation progress? And in the following, I'm gonna discuss two metrics. One metric is based on the rate at which join orders produce join result tuples. The other one is based at the rate at which join orders explore the space of possible join results. I'm gonna make that more concrete in the following, starting with the first metric. Now with this plot here, I compare two join orders for the same query. As you see, the green join order already finishes after 5 episodes, while the blue join order requires 10 episodes. And on the y-axis, you see the number of join result tuples produced per micro episode. And as you see, the number of result tuples varies over time. But if I look at the total number of join result tuples produced, which in this illustration corresponds to the area under those curves, then the total number of result tuples needs to be the same for both join orders since they process the same query. And that means if I divide the constant total number of result tuples by the number of episodes needed, I get the average number of result tuples produced per episode. And for join orders that execute faster, this average rate must be higher. So this simple metric allows us to identify better join orders. Now, the only problem with this metric is what happens if the join result is very sparse or even empty. In this case, this metric won't give me any information. So in the next slides, I'm going to discuss a metric which does not have this problem. Now I'm quickly going to have a look into the chat because I believe there might have been a question. How is it different than using dynamic sampling techniques used in some databases such as Oracle? So generally what we are doing here relates to sampling. When using sampling, you generally have two choices. You first of all need to choose how much to sample, and you need to choose what to sample. As long as you assume that different predicates in your query are uncorrelated, it would be sufficient to sample the different predicates independently and combine that into a selectivity estimate. But if you assume that predicates might have been correlated, then you need to sample specific predicate groups. And the predicate groups that become relevant depends on the join order that you are processing. So maybe actually let me quickly show one slide which relates to that. So here I have a little overview of some approaches that have been tried for join ordering. So the standard approach is that we use some kind of data statistics such as histograms and try to estimate the selectivity of predicates and therefore the intermediate result sizes for specific join orders before query execution starts. That is difficult in case of correlated predicates or UDF predicates where the optimizer needs to treat them as a black box essentially. What you can also do is to select some initial plan and then to try to re-optimize in case the plan is worse than what you expect it to be. Now, the problem with this is that first of all, you need to find some initial plan to start from, and how effective you are depends a little bit on the quality of that initial plan. It also means that you will not gather information about the plans that you are not executing. So if a different plan is much better than what you initially expected, you will not find that out if you don't execute it at all. And then what you can use, of course, is sampling, and that might relate to your question. So here I could try to estimate the selectivity of different predicates by sampling them. And here you have to make a choice about what you want to sample and how much you want to sample. Because, I mean, depending on the join order that you select, different intermediate results will get generated. So you would have to estimate the sizes of different intermediate results depending on which join order you want to perform. We essentially answer those questions, first of all, by interleaving execution and sampling, which means that we do not need to make a choice about how much sampling we do. And we use reinforcement learning in order to make good decisions about what to sample next in a way that gives us those nice formal guarantees. So that essentially is how we, so in the end, what we do is some kind of sampling, but we do not have a dedicated sampling phase and execution phase, but we interleave the two. So we essentially never stop sampling over the execution of the query. And at the same time, we use reinforcement learning in order to make the decisions about what to sample in the next episode, using a mechanism that gives us those nice formal guarantees that over time we will converge to near optimal join orders and essentially make near optimal evaluation progress per time unit. So does that answer the question? Awesome. Okay, good. So let me go back to the slide from before. It's a great question. All right. So for the moment, I'm introducing the metric that we use in order to converge to good join orders during query execution. And the first metric we have seen works well, but only if we have a join result of a certain size. If it is empty, then the metric doesn't help us at all. So let's see a metric which doesn't suffer from this problem. Let me quickly switch on the light here. So the metric that I'm going to discuss next is not based on the rate at which result tuples are produced, but it is based on the rate at which we explore the space of potential join results. So let's make that more concrete. Now, if I join those 4 tables here, I know, even before starting the query, that the join result tuples must be some subset of the Cartesian product between all of those tables, right? And the metric that we introduce is essentially based on the percentage of this superset of potential outputs that we have searched during one of those micro episodes. That's the high level concept. Now let's see a more specific example. Now, let's say that at the beginning of one of those micro episodes, we start from those currently selected tuples marked up in blue for each of the 4 tables joined. Now, during the episode, we make a progress of 2 tuples in the first table and 2 tuples in the third table in join order. Now, let's see what kind of reward we should calculate for this progress. Now, our depth-first join algorithm has the property that we only advance from one tuple in the first table to the next if we have completely considered all possibilities to combine the currently selected tuple with any of the tuples in the following tables, right? So if we make an advance by 2 tuples in the first table in join order, which here you have on the left-hand side of the screen, then we have implicitly considered and searched the Cartesian product between the first 2 tuples in the first table and all tuples in all of the following tables. And this Cartesian product, it selects 2 out of 5 tuples in the first table and then all tuples in the remaining tables. Therefore, we have covered 2 out of 5, meaning 40% of the space of potential join outputs. Now, we also made some progress for the currently selected tuple in the first and second table for the third table in join order, this one over here. Now, by advancing by 2 tuples in the third table in join order, we have implicitly searched the Cartesian product between the currently selected tuples in the first and second table and the 2 tuples in the third table that we have passed by, as well as all tuples in the last table in join order. So this corresponds to less progress than before, but still we want to count it. So here we are counting 1 out of 5 tuples in the first table times 1 out of 5 tuples in the second table times 2 out of 5 tuples in the third table times 5 out of 5 tuples in the last table. So altogether, this corresponds to 1.6% of the total Cartesian product space that we have searched here. And counting those together, we're making 41.6% progress during the current micro episode. Now, I know that in order to finish query evaluation, each join order needs to achieve 100% coverage, meaning we must have considered all potential join outputs, either concluding that there are no join outputs in one specific part of the space, or generating all associated join result tuples for some part of that Cartesian product space. Now, since all join orders need to cover 100% of the space of potential outputs, I can calculate the average rate at which a join order covers the space of potential outputs. And I know that by maximizing this average, I'm at the same time minimizing the number of episodes that this join order needs for execution. And because of that, this is also a metric that I can use in order to identify good join orders in average. Now, with those 2 metrics, I can execute one join order for one episode. I can measure the progress it makes. And of course, data is not perfectly homogeneous. So I will not always get the same progress per time unit, even for the same join order, but I will get something like a probability distribution over possible progress values, which in our case is proportional to reward. So each join order is associated with one reward distribution. And as I have justified before, we know that the join order with the highest mean reward is also the fastest join order to execute. But on the other side, there might be quite some variance, which might make it difficult to identify an optimal join order after executing join orders just for a few episodes, right? So at any point in time, we'll have some uncertainty about the true quality of join orders because we're only seeing samples. And this is exactly why we need a mechanism like the UCT algorithm, which is able to deal with that uncertainty in a principled manner and can optimally balance between exploration and exploitation in order to get near optimal expected reward over time. So this uncertainty on join order quality is precisely why we need the UCT algorithm or another reinforcement learning algorithm. So that concludes our wish list. Now we have early quality feedback, and that justifies that this join algorithm is probably a good choice to support our reinforcement learning approach. Now, we don't only want to identify optimal join orders, of course, we also want to generate a complete query result. And in order to make that efficient, we need to do some bookkeeping, which I introduced in the following. Now, there's two issues here. I mean, our final query result might be stitched together from result fragments that we generate in different episodes according to different join orders. So first of all, we want to make sure that the merged join result is correct. Also, we want to avoid redundant work across different join orders. So I'm going to discuss those 2 points in the following. Now, first of all, let's discuss about correctness. We essentially want the correct multiplicity for each join result tuple in our join result. So we definitely don't want less result tuples than would be correct, but also we don't want a higher multiplicity than in a correct query result. Guaranteeing that we generate each join result tuple at least once or with the multiplicity that is correct. That is fairly easy. We just need to use the coverage metric that I have introduced before and need to assure that at least one join order achieves 100% coverage of the space of potential join outputs. Then we have considered everything. In order to make sure that we don't produce redundant result tuples according to different join orders in different episodes, we need to track lineage, as I'm gonna describe in the following. Let's assume, for instance, that we are joining those 3 tables R, S, and T here. Now, let's assume we are processing a join order, which first of all identifies this combination of tuples marked up in blue as part of the join result. So we are adding this value combination 215 to our join result set. Now the join order continues processing and identifies another tuple which has the same values, but it is generated from different tuples in our base tables. So we are considering back semantics here, so we also need to add this tuple to our join result. Now let's assume that we switch to a different join order in the next episode, and that new join order starts processing from scratch again. So it might again consider the tuple combination marked up in blue and now also in pink again, and add one join result tuple, which should not be part of the accurate query result. Now, this tuple is redundant, but as long as we only look at the join result tuples themselves, we cannot really identify which of those 3 tuples is redundant and should be removed. In order to identify that, we look at the record IDs for the tuples in the base tables from which the join results have been generated from. And then we associate each of those join result tuples with lineage that represents from which tuples in base tables those join results have been generated from. And here I'm showing the lineage on the right-hand side. And that makes it fairly easy to verify that the blue and the pink join result tuples, that those are redundant and one of them should be deleted. So this is how we avoid producing redundant join result tuples according to different join orders. And now I believe there might have been another question. Let me quickly check. All right. Okay. So there's one question about the capabilities of verifying cardinality estimates offline, right? So that helps in certain cases, but first of all, you need to assume that your data doesn't change too dynamically. In our scenario, we don't use any information that has been collected before the query comes in, so we do not rely on that assumption. also, when deciding to verify specific cardinality estimates, you might be biased by the plans that have been selected in the past by your optimizer. That means that you might, in principle, miss out on good plans which look bad to the optimizer and therefore will never be selected. So assuming that you only have a limited amount of time that you can invest during the offline phase, you might miss out on verifying the cardinality of intermediate results that seem non-interesting, but actually are very interesting for efficient query plans. Yet another problem is that in order to leverage any kind of data statistics, you need some kind of information about the predicates which appear in your query. For instance, if you have certain user-defined functions that need to be treated as black boxes from the optimizer perspective, you might not know how to use your data statistics in order to estimate the cardinality for those. So with our approach, we treat essentially all query predicates by default as black boxes, because we don't make any assumptions a priori about what their selectivity might be. So this approach essentially does not care about whether your query predicates are formulated as a standard equality predicates, or whether they have been expressed as user-defined functions which have been freshly introduced. So I mean, all those things which leverage offline processing, and it doesn't really matter what you do at offline processing. It could be, for instance, using some training workload in order to train some machine learning based optimizer, or it could be just verifying cardinality estimates. All of this makes some assumptions that you know a priori what type of queries, what type of functions you will get at runtime, that your data remains relatively stable, and that you essentially, that you have some kind of information about which query plans are interesting. So I mean, all of this may work in certain scenarios or in many scenarios, but I mean, it makes certain strong assumptions that may be violated in practice. So it cannot give you the same formal guarantees that we are providing. And here there's another question about runtime adaptive plans. So in general, I was showing a point re-optimization in this prior work slide, where we essentially select some query plan to start with, and then we might switch to a different plan if we get feedback at runtime which tells us, for instance, that the current plan works significantly worse than what we have expected. So that means that in order to execute the start plan, you might already have some overheads, you already make some time investment. So this approach relies a little bit that you are able often to find a reasonable plan to start from, because if you switch to different join orders, you may not be able to reuse the intermediate results that you have generated. So there could be some significant overhead in the starting phase. Another problem is that with this approach, you can certainly find out if the selected query plan is worse than what you have expected, because suddenly some intermediate result that you believed to be small during query planning turns out to be huge in practice. So at that point, you can stop processing. But it will not give you information about different plans that you have not selected and that you are not executing, which might use different intermediate results. Perhaps there's a different plan which you have not selected for execution because you believe that it is very bad and has large intermediate results. But in practice, it would turn out that this plan is actually much better than what you expected. But if you don't execute it, and if the plan you execute doesn't share the relevant intermediate result with that other plan, then a runtime feedback will not show you that you could actually have selected a much better plan than the one you're executing, even if the plan you're executing is exactly as good as you expected it beforehand. Does that answer the questions? Okay, and also in our Sigmund paper, you find some comparison to re-optimization approaches, by the way, experimental comparisons. Okay, great questions. Now, here we are talking about how we can stitch together join results, result fragments that have been generated according to different join orders. We have justified where we need lineage in order to guarantee a correct result. Now let's look at the second point, which is that we want to avoid redundant work, because if we switch between different join orders and we start from scratch for each join order, that might actually become quite inefficient. And the main idea that we apply here is that we essentially fast forward the execution of a join order once we can guarantee that the result tuples it would generate have already been generated according to a different join order. So we skip combinations of tuples that have been considered before. Let's see how we can do this in a very simple case. Now here we are only joining two tables. So one of the possibilities is the join order first R, then S, which means that our fixed tuples in R iterating, perhaps with the help of some index structure, over the tuples in S in order to identify matching tuples. So I can represent query evaluation progress here by this two-dimensional plot. So here for a fixed tuple from R, I would consider different tuples from S, like here, and I would add the corresponding tuple combinations to my result set. And perhaps at this point, the current episode ends. So what you see from this plot is that there are certain tuples in R which I have already joined with all possible tuples from S. This is what we also call an offset. So the first few tuples from R, which have been joined with all tuples in S. And if I now switch to a different join order, which in this case must be S, first S, then R, I know that I never have to reconsider those tuples in R, which have already been joined with all tuples in S, because the corresponding result tuples have been added into our overall join result set. So that means that for one fixed tuple in S, I start after the offset in R and only consider the remaining tuples here. So I would do this here until the current episode ends. And at this point, I could do the same thing with S and identify those tuples from S that have been completely joined with all tuples in R and can be ignored in the future. Now, this is a simple version for the case of two tables. Let's see how we can generalize this to multiple joins. Now, let's say that we have a join order RSTU, which joins 4 tables. For the first table, as we have already seen, we can keep track of how many tuples have been completely processed, our offset. Now, for the second table, what we can do is that we keep track of which tuples have been completely processed given the currently selected tuple in R. Similarly for T, we can say which tuples from T have been completely considered, then combined with the currently selected tuples in R and S, and we can do the same thing for the last table. Now, this kind of progress can be stored in a tree data structure, which has nodes that are associated with join order prefixes. So here, for instance, we can store the offset for each table independently and as a function of the currently selected tuples in the prior tables in join order. So if we might have a join order RSTU marked in orange and a join order RSUT marked in green, if they have a common prefix, then I can completely share any progress that they achieve for the tables in this common prefix. And that turns out to be highly relevant in practice, because typically the UCT algorithm converges quite quickly for choices for the first few tables in join order. And with this approach, we can completely avoid redundant work when switching between those different join orders, as long as they share the first few tables. So this is ways in which we avoid redundant work across different join orders. Now, in our Sigmod paper, we describe a sequential version of the approach. We are currently working on parallel in-memory execution of this approach. So I'm going to give a quick overview of that ongoing work. Generally, we are interleaving optimization execution. So there's many ways in which we could exploit a parallelism. For instance, we could exploit parallelism by assigning different threads to different partitions of the join order space. So we would try out more join orders in parallel. Another possibility would be to break up the connection between query optimization and query execution and make certain threads entirely responsible for optimization and other threads entirely responsible for execution. So that would be a division with the green line. Or what we can also do is that for each currently selected join order during one micro episode, we execute it in parallel on different partitions of the data. So we are partitioning our database. What currently seems to work best is indeed this last approach, but we have to implement it in the right way. We are implementing this in an adaptation of our depth-first join algorithm that I'm quickly going to illustrate here. So with multiple threads, we would select one split table such that those multiple threads execute the same steps before the split table in join order. And then starting from the split table, they diverge and are responsible for different partitions in that split table and therefore produce a different non-overlapping result tuples. Now, as you see here, there is a little bit of redundant work being done for the first few tables before the split table. So you might be wondering why we not always select the leftmost table in join order as split table. And as long as data is uniform, that is actually a good idea. But if data is skewed, this might lead to one thread being responsible for some heavy hitter tuple, which overall is not a very efficient parallelization strategy. So instead of fixing the split table, we use a similar approach as we use for join orders. And we also adaptively change the split table in each episode. And we use runtime feedback in order to converge to optimal split tables. Now, this was a high-level overview of our approach. We also have a version publicly available on GitHub. It is still a sequential version, but if you ask us, we can also share the parallel version. And I think there might have been another question. Let me quickly look at that before discussing the experimental results. Okay, so basically, we detect the skew indirectly because if we select the wrong split table, we won't make that much progress. Does that answer the question? So, okay, essentially, at runtime, you can, I mean, if there is one thread which has been assigned a lot of, which has been assigned one heavy hitter tuple, let's say, then if choosing the wrong split table and some join order, we will observe that your overall progress per episode is not very high. So a different combination of join order and split table will probably give you more progress per time unit, because progress is essentially defined by the a thread that advances the slowest. And so since we, okay, there's some, okay, all right, good. Very good question. All right, good. So now let's quickly see some experimental results. You find the SkinnerDB implementation in that GitHub repository. And the current implementation focuses on analytical in-memory processing. It has a column store architecture, uses string compression and runtime throat generation, which are standard mechanisms, but it is interesting to know that you can combine them with this approach that I have just presented. Now, the most distinctive property of the implementation is certainly that it does not use any data statistics, no cardinality model, no cost model. Everything we do is based on information that we collect at runtime. So we use different benchmarks for our evaluation, which we classify into easy, moderately difficult, and very difficult benchmarks from the optimizer perspective. And that is based on how difficult it is to estimate the cardinality of intermediate results that appear when executing plans. For instance, for TPCH, data is synthetic and uniformly generated, so it is quite easy to estimate the cardinality. For the join order benchmark, that one operates on real data, so you do not have perfectly uniform data, which already makes it much harder to estimate the intermediate result cardinalities. And for the JCCH benchmark, which uses the same schema and queries as the TPCH benchmark, but it produces synthetic, highly skewed data, here selectivity and cardinality estimation is extremely difficult for the optimizer, so it typically goes wrong. And we are comparing here a SkinnerDB against some state-of-the-art analytical column store database system, and also against an adaptive processing baseline, which is focused on stream processing. And as you see here, once query optimization is very easy, we do pay some overheads. Once query optimization is moderately difficult, our approach already is competitive. If query optimization is difficult, then definitely our approach is much faster than the baselines. And before discussing that in more detail, let me quickly check out the chat. I think there might have been another question. Okay, so there's multiple questions which we might answer once at the end of the talk. Let me perhaps, okay. And yes, we do focus on all our workloads. There's 3 very interesting questions. I'm gonna come back to them at the end of the talk. Great questions. All right. Okay, and in order to just finish up the discussion of the experimental results, so here, some overheads for cases where query optimization is easy, but if query optimization is already moderately difficult, then this approach seems very competitive. Now, in order to illustrate the trade-offs here in more detail, let's have a look at those 2 figures over here, which apply to the medium difficult benchmark that we are using. On the left-hand side, we are measuring the processing overheads per intermediate result tuple. On the right-hand side, we measure the number of intermediate result tuples generated. We're comparing SkinnerDB against MongoDB, and as you see here, when looking at the overheads per tuple, SkinnerDB has higher overheads due to join order switching and learning. But if you look at the right-hand side, the number of intermediate result tuples generated is significantly lower because we are selecting better join orders. So for the medium difficult benchmark, those 2 effects kind of balance each other out. We have higher overheads per tuple, but we generate less tuples due to better join order choices. So both comes down to the same thing. Nice thing about our approach is that our performance is very robust towards different ways of formulating the same query. For instance, if we take just for fun the join order benchmark and replace all predicates or unary predicates by user-defined functions, then that has a big impact on traditional query optimizers because they might select join orders that are way worse than if they have more information. But in our case, it doesn't really matter because we assume by default that every predicate is a black box for us. Now, this is with user-defined functions, but even more moderate, semantically equivalent query rewritings. For instance, if you replace equality predicates by semantically equivalent like or in predicates, that can already trigger the selection of different join orders for traditional optimizers, while for SkinnerDB, every planning decision we make is based on intrinsic query properties and not on the way in which the query is formulated. If you break down the execution time into those different query evaluation phases that I have shown at the beginning, it turns out that like applying unary predicates and generating those join indexes account for a non-negligible execution time component, because in order to make exploring different join orders efficient, we essentially generate hash indexes on the join columns in order to support each possible join order. At least we only need to do this on tables that remain after applying unary predicates, but still it accounts for some overheads. The overhead of the post-processing phase for aggregation and for grouping depends a lot on the benchmark. It is higher for TPCH, for instance, than for the join order benchmark. The time for doing the join phase is always non-negligible. So in the following, I'm going to discuss primarily how we can optimize the join phase further. Now, first of all, the algorithm, the reinforcement learning algorithm we use matters. Random selections, for instance, definitely do not work well. We also compared the UCT algorithm with two other more recently proposed algorithms. The BRE algorithm, this one doesn't perform better than UCT, at least for the benchmarks that we have tried here. The reward function also plays a role. I have introduced two metrics for reward, and using a combination of both of them, like the average of them, tends to provide the most stable results according to those numbers here. We tried different ways of parallelizing the join phase, and as you see here, as announced, exploiting data parallelism works well, but it is very important how we select the split table, because if we do it in the wrong way, we don't get the speedups that we want. We also tried to instantiate our reinforcement learning approach on top of traditional execution engines, which we didn't expect to work too well, because all this join order switching creates certain overheads as they are not optimized for it. Here we're using the Postgres database system. And as you see here, compared to a well-tuned setup for Postgres when executing the join order benchmark, this is definitely slower. On the other side, if we consider essentially a non-tuned, like a Postgres setup without any manual tuning for this benchmark, then we can actually get faster. For instance, in the join order benchmark, as already pointed out by the authors that released the benchmark, Postgres has a tendency of selecting nested loop joins in cases where hash joins would be much more efficient based on erroneous cardinality estimates. You can avoid that by deactivating nested loop joins, and it's a simple change, but you have to know about it. And especially for novice users, that might actually be difficult to find out. In any case, using our specialized execution engine performs by many orders of magnitude better. All right. So this is some ongoing work. Here we have already discussed about parallel execution. We're also working on finding new approaches on top of existing database engines and on expanding the scope of decision making. We have focused on join ordering so far because that is a very impactful decision. But this approach seems quite generically applicable. So now we are considering using this to make different types of planning decisions as well. And also we have some projects on applying this approach for worst case optimal join algorithms. Before I conclude, I want to thank the entire SkinnerDB team. Several PhD students have been involved. They're all amazing. Also, several undergrads have been involved. In fact, the first version of SkinnerDB has been prepared by undergrads, and I'm very grateful to all of them. So in summary, I have shown an approach which combines adaptive processing with reinforcement learning, which has the disadvantage that you have certain overheads for learning and for join order switching. On the other side, you can select better plans for queries that are difficult to optimize, and your performance will be very robust towards different query rewritings. Thank you very much for your attention. Now I'm happy to answer more questions, or if you have to leave, then please feel free to reach out to me with more questions or visit my website for more ongoing research. Thank you. All right, already some people, thanks. I see the clapping icon, thank you. I see some people already announced that they want to ask some questions via mail, I'm very happy to answer to that. Also, I think we still had a couple of questions left from before. Okay. Okay, great question. So the question is, first of all, whether we target single machine database systems currently with this approach, in particular with our parallelization. And absolutely correct. Right now, we are focusing on shared memory, single machine architectures. We also have some ongoing work on distributed systems, but right now, those results, they refer to the single machine case. If you have a distributed system, then certain things become harder, already like dynamically changing between different switch tables, that might be harder. So yes, that would definitely require a different approach, yeah? And I mentioned that the method doesn't rely on historical data, but upper confidence bounds seem historical. Actually, so by historical data, I mean data from executing past queries. Those upper confidence bounds, they are initialized from scratch and only use information that has been gathered during the current query execution. So we also don't make any assumptions that the same query is executed repeatedly. We only assume some fresh query that we have never seen before comes in. At the beginning, we don't know anything whatsoever. And then over those thousands, 10,000s, 100,000s of micro episodes, which are very fast, we learn something about the query. And that is the information we use for those confidence bounds. But absolutely no historical information in the sense of like anything gathered from different query executions. Everything we use is from the current query execution. And that ensures that it, first of all, is immediately relevant for the current query. And also it refers to the current version of your database. That is the advantage. You may have mentioned, but what's one episode? Is it like 10 tuples or running 10 seconds? Okay, so for episodes, we define episodes slightly differently in the version of our system that uses the specialized execution engine and in the version that runs on top of Postgres, for instance. But in our main variant, where we use a specialized execution engine, one episode is currently defined as 500 steps, where one step corresponds to one lookup in an in-memory hash table, for instance. So the thing is, we could in principle use immediately just like the time measurements from our machine, and we could just switch after a certain number of milli or microseconds. The problem is that we want to have a very high switching frequency, like 10,000, hundreds of thousands of times per second. So that means it becomes very hard to measure time reliably at that granularity. And this is why we use the number of computational steps as a proxy for time. So one episode is 500 computational steps for our main variant. For the variant on top of Postgres, just because Postgres is not optimized for this join order switching and so on, we say that one episode tries to process one very small batch of data with a certain timeout. And choosing the timeout, we also don't know what timeout is good at the beginning, so we will cycle through different timeouts according to a specific system which is described in the paper, and which comes with some nice formal properties. Okay, please let me know if there's any follow-up questions. Okay, I'm just gonna iterate over other questions that have been coming. Okay, thanks, that's yes, very happy to. Okay, couldn't there be some data distribution that make the learning fail? Okay, that is a great question. So the guarantees that we have are based on the guarantees of the UCT algorithm, and the UCT algorithm makes the assumption that the reward distribution that is associated with certain action sequences remains the same. So you always get different rewards, but the distribution of the rewards does not change over time. So that is why we assume that the data is not ordered in some specific way, which makes one join order preferable at the beginning of execution and a different join order at the end of execution. So that could be achieved by just shuffling your data, basically. So right now, we assume that the data is randomly distributed. Of course, there can be variations. So we don't assume data to be homogeneous. We assume that progress you get for a fixed join order in different episodes might vary a lot. This is exactly why we use reinforcement learning in the first place. But yeah, we assume that the reward distribution remains the same. Does that answer the question? Awesome. Any other questions? Okay, I guess there might not be any more questions for the moment. Or maybe. Okay, thank you very much. Great questions, great discussion. Thanks a lot for the invitation. All right. And let me know if any questions come up later. Happy to answer them via mail. All right. Thank you very much.